Welcome and thank you for joining me. Today, we'll continue with lesson U1L7, Graphing Polynomial Functions. In this lesson, we are going to learn how to perform a complete curve analysis of polynomial functions. By the end of the lesson, you'll be able to analyze and sketch the graph of any polynomial function by applying all the concepts that we have learned throughout this unit. So let's begin with our curve sketching algorithm. The first step is to determine the domain and range. The domain is the easiest part because every polynomial function has a domain of all real numbers. For the range, I will check with one thing first. If the polynomial is odd degree, then the range is automatically all real numbers, since the graph will extend infinitely in both positive and negative y directions. If the polynomial is even degree, don't determine the range immediately. An even degree polynomial function may have an absolute minimum or an absolute maximum, and that will limit the range to a specific set of y values. So therefore, I would suggest that we first start by sketching the graph, finding where the max or min is, and then determine the range. Next, we'll find the intercepts, both the x and the y intercepts. As you determine the x-intercepts, be sure to identify also the multiplicity of zeros. Now, for the y-intercept, we set x equal to 0, evaluate y, whereas for x-intercept, we set y equal to 0 and then solve each factor for x. Remember that in order to find the x-intercepts in a polynomial function, we need to have the graph in factored form. Now, when it comes to multiplicity, we have to be looking for different types of multiplicity. And the main ones we look for are multiplicity of 1, where the graph will intersect the x-axis, like straightforwardly. A multiplicity of order 2, the graph will make a turn on the x-axis. And when the graph has a factor of multiplicity of 3, then the graph will make an S shape at the x-intercept. Now, as multiplicity increases, then the graph will be flatter at the x-intercepts, but the shape will be similar. Our next step is to check for symmetry. We'll begin by testing even symmetry by finding f of negative x and comparing it with f of x. If they have the same values, then we'll say the function has even symmetry. If not, then we'll check for odd symmetry by simply taking f of negative x and switching the sign of every term in it, or finding the opposite of it. Then we compare negative f of negative x with the given function f of x, and if they're equal, then the graph of the function will show odd symmetry. And if not, then we're going to say that the function has no symmetry at all. Next, we'll determine the end behavior. For even degree polynomial functions, the end behavior will depend on the leading coefficient, whether it is positive or negative. If the leading coefficient is positive, then at both left and right end, the graph will head to positive infinity, so the y values will approach positive infinity. If the coefficient a, the leading coefficient a, is negative, then the graph will open down, and at both ends, left and right, the y values will approach negative infinity. For odd degree polynomial functions, if a is positive, then the function will approach negative infinity in the left end and positive infinity in the right end. And if the leading coefficient is negative, then the function will approach positive infinity on the left end and negative infinity on the right end. Next, we determine the absolute minimum and absolute maximum along with local min and maximum points. Now, we'll spend a little extra time on this step because I have a strategy that makes finding these points much easier and more accurately. And finally, we'll determine the intervals where the function is positive or negative. The function is positive for the x values where the graph is above the x-axis, and it is negative for the x values where the graph of the function is below the x-axis. Now, once we have completed all these steps, we'll have everything we need to draw an accurate sketch of the polynomial function. Now, as you obtain each piece of information, don't wait until the end to start drawing the graph. Build your sketch as you go. Each new feature helps refine the graph, making the final sketch much easier and more accurate. And each step, when completed, will lead you to a better understanding of when, where, and how to find or to determine the measurements of the next steps. Also, when determining max and min points, you may sometimes obtain decimal values, and that is perfectly acceptable when you're using those values to approximate the location of turning points on your sketch. But whenever possible, determine the exact value. But if an exact value isn't practical, a decimal approximation is completely fine. So let's get started with our first example. The function f of x equals x minus 3, x plus 3, x plus 1. I'll start off with the domain. It's a polynomial function, so the domain is a set of all real numbers. Next, we'll look into the range. Now, this function is given in factored form, and the factor of x minus 3 has a multiplicity of 1, x plus 3 multiplicity of 1, and x plus 1 also has a multiplicity of 1. So that will make the degree of this polynomial function equal to 1 plus 1 plus 1, or 3. And that tells us that this is an odd degree polynomial function. Now, in odd degree polynomial functions, we're ready to state the range right away, and we're going to say y is any real number. Next, we'll find the x-intercepts. For x-intercepts, we're going to make y, or f of x, equal to 0. So 0 equals x minus 3, x plus 3, and then x plus 1. And just like we found the zeros of quadratic functions in grade 10 and 11, now we're going to find the zeros of a higher degree polynomial functions by setting each factor equal to 0 and solving for x. So we're going to write x minus 3 equals 0, x plus 3 equals 0, x plus 1 equals 0, and isolate x. So we see that x equals 3, negative 3, and negative 1. So these will make the x-intercepts of the function, which we can write as ordered pairs. And I prefer to write them from lowest to highest value. And that is because it makes it a lot easier for me when I plot these points on the Cartesian plane. It's not hard regardless, but it is a little bit more practical, so it's recommended but not a must. Another way of writing the x-intercept, totally acceptable again, just write x-intercept is negative 3, but be sure that you clearly separate each x-intercept by a comma, and negative 1 and 3, and that would be it. For the y-intercept, we are setting x equal to 0 and then evaluate the function. Or evaluate the y in the function, which means that we are trying to find in here f of 0, which is 0 minus 3, and 0 plus 3, and 0 plus 1. As you can see from every factor, we are left off with constants only. So what does that mean? It means that the y-intercept is practically the product of the constant terms in a function. And these are very important patterns to recognize, because they will help you to factor polynomial functions in the near future, in the upcoming lessons. So as you can see here, we have the y-intercept of negative 9. Again, we can write this as an ordered pair, so 0, negative 9, or we can simply state that y-intercept is negative 9. So next we have to determine intervals of increase and decrease. Now remember that for intervals of increase and decrease, we're going to need to know the minimum and the maximum points on the graph. Remember that a function is increasing up to the maximum and it is decreasing up to the minimum. So the min and the max are the key values. And we said that we're going to save this for last because it requires a little bit of more tedious work. Now, next we want to determine where the y values are positive or 0 in this case, and negative. So I think it's time for us to plot on the graph all the numbers that we have determined so far. We do have the x-intercepts, which are at -3, -1, and +3. So here is the x-intercept of -3, -1, and then +3. We have also determined the y-intercept, which is at -9. We know that the degree of the polynomial function is odd, and if we want to start sketching the graph, we need to consider the leading coefficient as well. Remember that the leading coefficient is the product of the leading coefficients in each factor, and in other case, the leading coefficient will be equal to 1 times 1 times 1, which makes a +1, and we're going to say that this is an odd degree polynomial function with a positive leading coefficient, and it tells us that this graph will start in quadrant 3 and end in quadrant 1, just like a line with a positive slope. So I am going to use the pencil on my paper and pencil handout or notes and lightly kind of draw the graph of this function. Now, as you can see, we are able to tell what the end behaviors are at this point, and we are able to tell where the graph is above and where is below the x-axis. So we can determine the intervals where the y is positive or negative, and we can also determine the end behavior. So let's get to work. Now remember that we still don't know the min and the max. We're going to do that very soon. So we're going to say that the graph is positive or 0 where it's above the x-axis. So the x values for which the graph will have positive y values are between -3 and -1. So we're going to write that down. And as you can see in here, we are also asked to find where y is also 0, which means that -3 and -1 will be included in the intervals where y is positive or equal to 0. Now, the graph of the function is also positive for the x values that are greater than 3. So we're going to say we need to join the interval from +3 all the way to infinity. Now the graph is negative. Let's take a look. Below the x-axis, and that will happen for the x values from -infinity to -3. So let's write this down. Remember, we don't need the 0, so therefore we're going to keep -3 in the inside round brackets, and then we'll join to this interval the next one where y is negative, which is between x -1 and +3. So again, we're not interested in the 0, so -1 and +3 will be both inside round brackets. Now, next we have to determine the end behaviors, and that is because we can. Now, the end behaviors on the left side is where x approaches -infinity. You see the y values are dipping down, so we're going to say that when x approaches -infinity, the y values will approach -infinity. And on the right hand side, x approaches +infinity, y is going higher and higher, which means that the y values are approaching +infinity. And now for the fun part, we have to determine all the minimums and the maximums, and that will help us determine and define the intervals of increase and decrease. Now, fair warning, brace up for some tedious work, but interesting in the meantime and quite logical. So, when I look at the sketch of my graph, obviously this is not the final graph that we want to show, we see that the graph seems to have a local maximum and a local minimum. Now, because this is an odd degree polynomial function, there are no absolute min and max. Only even degree functions can have absolute min or absolute max. So we're going to complete the chart in here because why not? We've already figured that out. So there will be no absolute maximum and no absolute minimum. Now, very often students will write no absolute maximum and just write a number 0 here, or no absolute minimum. Now, we don't want to do that. And the reason why because when you write the 0, meaning that there are 0 number of absolute maximums, we may think that, oh, there is an absolute maximum of 0 or an absolute minimum of 0. 0 is a number, and numbers have a very meaningful kind of attitude towards in mathematics, so we have to use them very precisely. So it is more practical and accurate to just simply say none, and if you want to write not applicable, that is totally fine as well. Now, we're going to find the local maximum first, which seems to be somewhere in here. Now we are thinking, if there is a local maximum, where could it be? Usually polynomial functions do follow some predictable trends, and what we do in this case is we look in between the x-intercepts where the local maximum is located, and as a guiding value we're going to check x equals -2, and we'll try to evaluate the function at x equals -2. So we're finding the local maximum, and I'm just going to write down here every step what I'm finding and how. So I'm going to evaluate the function at -2. This is going to be my guiding x value for the maximum, or a guiding point that is a little bit more general. And where do I get that? Halfway the x-intercepts. So I don't just pick and choose because I like a number, right? Halfway between the two consecutive x-intercepts. So we'll do that. We'll find f of -2 for the function that is x plus 3, x minus 3, and then x plus 1. So as you can see, instead of x, now we have written the value where we're evaluating the function n. So that will give 1 times -5, and then times -2, and that will be equal to, sorry, my bad here. So -1, and that will give a 5. So we're going to say that f of -2 is 5, and it is totally fine, totally acceptable to plot that point because it will indeed be a point on the graph. So that would be the value of the function. 5 will be the value of the function at 5. Now, we're not sure whether the function is going a little bit higher and coming back at 5 and hitting the x-intercept, or if the function is going a little bit higher on the right side of it and then coming down. So what we're going to do is we're going to check and see what happens to the right of -2. So what's the value of the function? Will the function go higher or lower? So to the right of -2, we have the number -1.9. So we'll try to evaluate the function at -1.9. And that will give -1.9 plus 3, -1.9 minus 3, and -1.9 plus 1. So as I mentioned before, this is a little bit of a tedious process, but still logical. So let me grab a calculator. And determine the exact value of the function at this point. So -1 plus -1.9 plus 3 would be 1.1. -1.9 minus 3, -4.9, and -1.9 plus 1 is -0.9. See what this product will become. So we have 1.1 times -4.9, and then multiplied by -0.9. And what I get in here is 4.851. So what that means is that this point in the middle is higher, which means that if there is any higher point, we have to look for the left side of negative 2. So I'm going to try to find f of negative 2.1. So again, negative 2.1 plus 3, negative 2.1 minus 3, and negative 2.1 plus 1. So this would be 0.9, negative 5.1, and lastly we have negative 1.1. Let's see what we get here. So 0.9 positive multiplying negative 5.1 and multiplying negative 1.1. So that is equal to 5.049. The truth is that there is no much of a difference really. So it's not even 0.1. It's like 0.005. So 0.05 higher. But it is higher than negative 2, which tells us that the graph will have a higher point in here, and I'm exaggerating this a little bit for the purpose of explaining the logic of it, but it seems that negative 2 is not the highest point on the graph. Now, to make sure that I have hit the maximum, the highest point I can, I'm going to go a little bit deeper into the negatives to see if there is a point higher as we move on to the left. So negative 2.2 plus 1. Let's see what we get here. So I'm going to try to calculate this in one step to save our time. Negative 2.2 plus 3. Multiplying negative 2.2 minus 3. And then multiplying negative 2.2 plus 1. And I get indeed okay, negative 2.2, okay, so brackets here, 4.999. So as you can see, after negative 2.1, which we marked as the higher point, we see that the graph of the function now is coming back down, and that tells us that this would be the highest point, and we're going to say that the graph of this function, will be heading down this way, and this would be the highest point. So the local maximum in this case will be at x equals negative 2.1, y equals 5.049. So negative 2.1, 5.049, and obviously I'm going to write this information at the local maximum spot in here. So we're going to say local maximum is at negative 2.1, 5.049. Now next we'll find the local minimum. Now the local minimum, as you can see here, is down here between the x-intercepts of negative 1 and 3. So again, the same strategy. We're going to choose a number in the number in the middle of the two consecutive x-intercepts, and it seems that we have number 1 in here. So our guiding point will be at x equals 1. So we're finding the local minimum. But you see that when you put the information down here on the grid, you kind of know what you're looking for. You're looking for a higher point, or you're looking for a lower point. And when you are trying to find these y values, you know that whether you're looking for a point higher than the one in the middle or lower than the one in the middle. So you get the idea of why we do what we are doing here, I hope. Now, at x equals 1, so we're going to use x equals 1 as our guiding point, which is halfway between x-intercepts of negative 1 and x-intercept of positive 3. So at x equals 1, this is going to be super easy to evaluate. We have 1 plus 3, 1 minus 3, and then 1 plus 1. And we get 4 here, we get negative 2 here, positive 2 here, and that will take us all the way down to negative 16. So we are going to now delete the highlighted graph because we have more accurate information coming. So at negative 16, all the way down here, and positive 1, we're going to hit one of the points on the graph of the function. And what I'm going to do now, since we're at it, I am going to let the function flow, hit the y-intercept at -9, and I'll be patient in here for this. So we want to check and see whether the graph goes down and then up in here, or whether the graph will go down and then further down and then get up again. So for this, what I'm going to do is I'll check the x values to the right of 1. So we'll find f of 1.1 to check and see whether the graph of this function will go a little lower on the right end, 1.1 minus 3, and then 1.1 plus 1. So what we have here is 4.1 multiplying negative 2.9, and then multiplying 2.2, and that will give us, sorry, my bad here, sorry. Good. All right. Got too excited there. So we're going to multiply now 4.1 by negative 1.9 and then by 2.1. And we get negative 16.1. So we're going to get here negative 16.359. So what that tells us is that the graph of this function is going further down as x becomes bigger than 1. So I will plot this point, negative 16. So it's going to be a point somewhere. I don't know if you can see it somewhere in here. Again, it's a bit of an exaggeration. It's not properly scaled, but just for the purpose of understanding where the points are going. So if I were to check for smaller y values, I would keep on searching for x values greater than 1, because it seems that the graph of this function is indeed following this trend. And I'm going to check and see at 1.2 what's happening to this graph. So we have 1.2 plus 3 and 1.2 minus 3 and 1.2 plus 1. Now, fair warning, whenever you determine these values, you don't have to show the work the way I am. You can simply state the values that you have checked, and I mean f of 1.1 is equal to this number. Just simply use a calculator. It is a lot of work to show, and it is repetitive for sure. So we have in here 4.2, and that is multiplying negative 1.8 and multiplying 2.2. See what we get. 4.2 times negative 1.8 times 2.2. I got negative 16.63. I got an even smaller number, which means that I should check for 1.3. Let's see what we get there. 1.3 plus 3, 1.3 minus 3, and then 1.3 plus 1. So that would be 4.3 multiplying negative 1.7 and multiplying 2.3. So minus 3, and then the answer is negative 16.8. Okay, so we are being challenged here, I believe. So we have even a smaller negative, so it seems that we are continuing to go further down in here, and we're continuing with one more value. I think that we're coming very, very, very close to the actual minimum. So let's see. So what we are hoping for here, while we're at it, what we are hoping for here is finding a y value that is now, here is a negative. So finding a y value that is less than negative than this. So we're going to do f of 1.4. So that's going to be 1.4 plus 3, 1.4 minus 3, and then 1.4 plus 1. So let's calculate this in one step. 1.4 plus 3, multiplying 1.4 minus 3, and then multiplying 1.4 plus 1, and I got negative 16.89, which is about negative 16.9. Now, another thing I wanted to mention is, you see that as we went here 0.1 for greater for x, we saw quite a difference, well, considering, all things considering, a difference in the y values. But you see now 16.8 and 16.89, that gap is kind of narrowing down. So you see that the reason for it would be because we're getting really, really close to the very minimum. So I believe the next point will be a less negative number. But let's do this just for the fun of it. So 1.4 minus 3 and 1.4 plus 1. And let's see what we get. We have 1.5 plus 3, multiplying 1.5 minus 3, and then multiplying 1.5 plus 1. And I got negative 16.87 this time. And what that means is that the function is coming back up, and our lowest point on the graph, at least the lowest that we can estimate at this point, will be when x equals 1.4 and y equals negative 16.9. And that's a point that we want to actually draw with more accuracy here. So 1.4 will be somewhere a little bit closer to 1, but somewhere in the middle between 1 and 2, and 16.9 will be very close to 17, but slightly above it. So I'm going to mark in here just the very minimum. So I will obviously leave the 1 in here and 16.9. So that's exactly where the minimum will be. And for the rest of the graph, we simply connect the points in a smoother curve. Okay, and we're going to go all the way back up. Let's try to make this nice and round. And extend the graph here. Obviously, do not go wild here. Just smoothly continue drawing the curve. And this would be the graph of this polynomial function, and the local minimum would be at the point with coordinates we said 1.4 and 16.9 negative. And we're going to plot this point on the chart. So there is a local minimum at 1.4 and negative 16.9. So now it's a lot easier for us to determine the intervals of increase and decrease. Notice how the function is increasing, and then it is decreasing, and then increasing again. So the x values where the increasing and decreasing intervals are separated from each other are at the maximum and the minimum. So we're going to say that increasing from negative infinity to negative 2.1 and increasing from 1.4 to infinity. So we're going to say that the x values will be between these two intervals, and intervals of decrease will be for the x values between the local max and local min, which is negative 2.1 and 1.4. So negative 2.1 comma 1.4. And when we state intervals of increase and decrease, very important, we always use round brackets, and that is because the points where the two are separated are not included. At these points, the function is neither increasing or decreasing. There is a moment on the graph that when it goes from increasing to decreasing, it stops changing, and that's why we use the round brackets there. So this is a complete analysis of a polynomial function. We looked at a third-degree polynomial function, and I hope you found the instructions useful, and I invite you to continue trying the next examples on your own, and I will continue completing and explaining this in the next video. And until then, bye for now, and thank you for learning with me.